This task calls for a function that will calculate the total bill after a customer has used a number of units of electricity. So we begin by constructing the outline of the function, and we're going to mark it as private and static, not two words that a GCSE student would need to understand, so you can just casually ignore those. We're going to be returning a real number here because we're going to be dealing with an amount of money given in pounds, so it's going to have a pounds part and a pence part, so the double data type is the best fit in this case. Let's call the function calculate bill, and the value that we're going to be passing into it is the number of units of electricity used. Now, this gives food for thought. Should we include a decimal part or not? In order to add the most flexibility, we can pass it in as a double, but thanks to implicit typecasting in Java, when we call this function, we can provide it with either an integer or a real number as a parameter, and the Java language will automatically convert it and switch it over to being in the double data type for us, regardless of which particular integer data type or real number data type we use. So we have 6 choices, and all of them will get upgraded to being a double. So we begin by saying that if the number of units used is somewhere between 0 units and 120 units, then that means that we very simply multiply the number of units used by 38.2 pence. So straight away we can say that if the number of units used is less than or equal to 120 units, then that means that we're going to end up charging the standard rate. And so before we launch into the if statement, let's set up a price variable, and inside here let's say price becomes equal to the unit price of 38.2 pence multiplied by the number of units used. So that's a very straightforward process calculating the overall price. Now, in the event that the number of units is greater than 120, well, this is just the opposite of less than or equal to. So we can put this inside an else statement, and we can say that in this case the price is going to be 38.2 pence multiplied by 120 units, and that chops off the first 120 and charges for the first 120 units only. But we know, if we are in the else block, that the number of units used is greater than 120, and so we have to add on the price of the remaining units. And to calculate the remaining units, we take the number of units and we subtract the 120 that we have already charged for. The price of those additional units is 36.1 pence according to the task. So, having calculated the price before tax is added, we have now got 2 situations. One of them where the number of units is just very simply a number up to and including 120, but alternatively we could be looking at a much higher number, therefore you charge 38.2 pence for the first 120, but a different rate for the remaining amount. And it's that job of separating out the remaining amount that solves this problem. Next, we're going to have to add VAT. Now, if you start with 100% of the price and you add 5% of the price, that brings you to 105%, which can also be written as 1.05 in decimal form. Therefore, what we can do is we can take the price and we can say that it becomes equal to the price multiplied by 1.05. Now, that will inflate the price to 5/100ths higher than it was before, thus adding 5%. At the last minute, what we then need to do is we need to say, well, the price, if we were to return it now, it would be given in pence, but we need to give it in pounds. And if we're going to give it in pounds, then that means that we're going to have to divide it down by 100. So we're going to use the normal divide operator, and we're going to divide it by the real number 100 so that everything is kept in the double data type. And it's nice and clear that we're sticking to the double data type in this case. So we could also move the division by 100 up to here, and if you look again with fresh eyes, you'll see that when you multiply a number by 1.05 and then divide by 100, well, that would have the effect of moving the decimal point 2 places along. And so we could write this as 0.0105 and do away with the division by 100 here and do away with the division by 100 here. Now, some would argue that that would make for a less readable program, and indeed we could even put the return statement here, and that would mean that we've got in pounds with VAT added. We've got a slightly more complex formula in front of us. However, if you would prefer to unravel this and leave it as it originally was, we can just do a series of undo statements here and put it back to how it was previously, and we can say that so we can say that what we did in this case was we add the VAT here and then we convert it into pounds on this line whilst we're in the process of returning it. So this gives us a working solution to the problem, the original problem statement, that we can now test. In order to test this function, we recognize that it is a function, therefore calling it on its own as a line of code isn't a very effective way to do it. So let's begin with a number that is less than 120, let's say 64. Now, whilst it's giving us like a little bit of a warning, it's not telling us that we've done anything terribly wrong. It's advising us that we need to perhaps assign the returned value to a new variable. But what we'll do is we'll just print it, and then that means that we can see the results on the console screen and we know exactly where we stand then. So let's take a copy of that and let's put in 3 or 4 other test cases. Let's put in a boundary case of 120. Let's put in a much larger number which is above 120, and then let's try just feeding in 0 units. If the customer uses 0 units, do they get charged £0? Okay, so let's run the program and just observe what the outputs are. If we compare this like for like, let's see, so the 64 units is going to cost 25.67 pence. 120 units is going to charge £48 and 13 pence if we were to round that. 247 is going to cost £96.27 pence, and 0 is indeed coming out with a bill of £0 and 0 pence, which is healthy. Now, in order to show these values with 2 decimal places of precision, then what we can do is we can bring in the concept of decimal format. So decimal format is a special class in the Java language. As you can see, it's given angry red underlining here in the NetBeans IDE because it says that it cannot find this class. So we can use the IDE to help us here, and we can add an import statement. The import statement has now been introduced up at the top, allowing us to do our 2 decimal places option. So what we do is we build a variable called df, and that variable is new decimal format, and we've put in a string pattern here that uses 2 decimal places. So from now on, when we want to write down our output of our bill, we use df.format, and if we trap what we were trying to print inside round brackets, it will then automatically format it to 2 decimal places. And I'm just pasting in the opening part, and now I'm adding that extra bracket that each line needs in order to close the df.format's opening bracket. There you can see it becomes the middle bracket in each expression. And let's just rerun the program, and you can see that we've ended up with our values now with 2 decimal places. And what we can even do now is put in a pound sign and just concatenate the, maybe space that out a bit for neatness, put in the pound sign and allow it to look like an amount of money. We will have a little bit of awkwardness with the £0 sometimes, but in this case it has formatted it to precisely 2 decimal places, which is brilliant. Okay, so one other revision, or a couple of other revisions of our solution to the problem here. The problem really focused on the function, and so one of the things that could go wrong is that the user could input a negative value. Now, we could assume that the values are always valid, but just in the case that they maybe enter, for example, a negative value, we could say if the number of units entered is less than 0, then what we can do is we can output an error message, and we can say invalid units entered. And then we'll have to return some sort of a value. So we could return 0 in this case, rather than, we could use -1 as well. Some sort of dummy value that is not really going to be used ever, and it's something that the main program can catch then as part of its own work. Another aspect of the problem, earlier on I showed that we could tidy this up and compress it down into one line of code by combining multiply by 1.05 and divide by 100 into a single operation by simply dividing that number by 100 and multiplying by that instead. And we could even move the word return up so that we don't update the variable any further. Another idea would be to simplify this expression. So if we look at this expression and take a copy of it, let's take out just a simple notepad document and just take a kind of a closer look at it. So what we're dealing with here is we're dealing with some numbers, and there's only really one algebraic term, one variable here, but everything else is just a number. So let's look what happens whenever we try to simplify this. If we call up the calculator on our screen, let's call up the calculator, and what we can do is we can start off with 38.2 multiplied by 120, and you can see here that we can just put in the literal value 4,584 in its place. I'll take out the comma. Then over on the other side we can see that we're dealing with a number 36.1 being multiplied by a bracketed expression, and so what we can do is distribute the 36.1 into both of the terms inside the bracket, and that will extract one more literal number. So we've got our original 4,584, then we're going to add that to 36.1 times the number of units. Now we see a positive number being multiplied by a negative number here, so the result is going to be negative. The size of the number will be 36.1 multiplied by 120. For an easy life, 36.1 multiplied by 120 is going to give us 4,332. And so if we look at our expression again, for simplicity we can rearrange this so we can move the numeric parts so that they are side by side, just for ease of reading, because it's convenient to do that when you're on a computer. You can see that these two literal numbers can now be simplified themselves. We can simply knock out the 4,000s from each one because subtraction will knock them out. We can take the 500 and take away the 300, and that gives us 5 take away 3 is 2, and then the 300 will simply disappear. 80 take away 30 will give you 50, so we can reduce the 8 down to a 5, and that will subtract 30 from 32, leaving just the 2. And finally, 254 take away the 2 will give you 2, and then that eliminates that number entirely. And so we've reached a much simpler version of our expression. Now if we were to bring that back into the code, it will simplify the work that the computer has to do, and it will therefore make the function operate more efficiently. But there is an argument to say that we have therefore reduced the readability of the program. So we could put in a comment here to say simplified from, and then we can put in the original expression, which we still have in our notepad document here. And that just helps a developer to kind of read this and see where the original expression came from. Okay, so that would complete the task then, and we have a fairly robust program. We'll just test it one more time because we've made some changes. And yes, those numbers do look the same as the previous numbers. And that's it for that function. The task was really to construct the function. It goes beyond the scope of the task to do things like, extensive simplification and decimal format to 2 decimal places and so on, but it's some Java skills anyway that do come up from time to time, so it's good to know what to do, and bear in mind that the decimal format class in Java does have to be imported from the java.txt library before it can be used.